So welcome back to the second lecture segment of Chem 580, the spectroscopy course. We are going to start our review or summary of basic quantum mechanics so that we have a common vocabulary to use to continue for the rest of the semester. There's no real spectroscopy without quantum mechanics one way or the other. We can talk maybe later at the end about methods of semi-classical approaches to doing spectroscopy. But if we're really talking about energy levels in molecules, then there's no way around the fact that there's going to be some kind of quantum mechanics involved. As I've said before, we can almost always treat the field classically, so we don't need to rely on quantum mechanics for the light. A little bit later, when we learn about fluorescence, though, inevitably there's not much you can do to understand fluorescence without admitting something about the light field of the vacuum, so-called electromagnetic vacuum, and that is what's going to lead to the emission of fluorescence. Right? So you're coupling an excited state to a vacuum of electromagnetic modes, and it's the number of modes per frequency that gives you fluorescence. Okay, so we're going to start right now with the basic postulates of quantum mechanics, which you could review in any book that you might have. What do I use? Well, I had a pretty excellent quantum mechanics professor when I was in graduate school, Paul Bremer, and he liked an old book by Albert Messier, I guess it would be in French, Messier, however one says it. It's an old book from French that was translated into English, so it's a little hard to read. But I liked it. It's really very rigorous, even if some of the later parts of it are out of date, because in 1950s I didn't know everything, especially in physics. And so I like that book, but there are many, many, many others. So whatever you like, Cohen Tanuji or any of the many, many quantum textbooks. The only issue is when you switch from book to book, the notation is almost always going to change, and that's sort of annoying. Another book that gets you through the beginning of quantum mechanics quickly, and it's probably the narrative that I followed, was the book by Shaul Mukamel on nonlinear spectroscopy, and it starts out this way, you know, reviewing basic quantum mechanics. So you can try Shaul's book. It's called Principles of Nonlinear Optical Spectroscopy from 1995, which I can't believe I'm saying that. When I was a graduate student, I saw somebody had I think the galley proof of his book is photocopied in a loose leaf binder. It's now over 25 years old, but it has been very useful for many people in our community. All right, so what are we going to do? We're going to start out with the basic postulates of quantum mechanics. All right, so postulate number one basically is that you have the state of a system, which is described by the state vector psi, which is usually the notation for that. And from this state vector, you can calculate any property of a system, right? You might have not used that terminology, state vector, before. You might have called it a wave function, if you will. They all mean the same thing, all right? They mean the actual state of the quantum system is somehow specified, and once you do that, in principle, you can use that to determine all of the information of the system. Now, sometimes you might see this in a representation. That's an important word. I'll just abbreviate it here, rep. So I like to think of the vectors as, you know, pointing somewhere in this space that's called Hilbert space, and we have a choice of how we choose to kind of take that information and convert it into, let's say, a human readable form. Right? Well, one human readable form is to project that Hilbert space wave function onto the position representation. Right? So we would convert the vector in Hilbert space into something like a position vector. It could be one-dimensional, two-dimensional, it could have 5 particles, each one of them having 3 dimensions, and so on. That's what's encoded in this R vector here. It is a spatial function. All right? It could be time-dependent, of course. We'll develop that too. So it might have position and time. Okay, but the point is there's no rule that says you have to do it this way. You could have chosen, for whatever reason, to project this into a different representation. For example, you could have taken the momentum representation, in which case the function will probably be different, and it will be a function of momentum. which would also be, for example, a function of momentum and time. These are different representations. We would call this in the position representation, in the momentum representation. You might say, when are we ever going to use momentum representation? Well, if you do anything where the potential energy function is periodic, it turns out it's very convenient to work in the momentum representation. So if you ever happen to meet a condensed matter physicist, they will probably talk about things like wave vectors. Right? And the reason for that is because it turns out it's much more convenient to talk about things in the momentum representation, K space or K, they sometimes use instead of P, but it's the same thing. And it's because of the periodic potential. Whereas in chemistry, we like to talk about where, sort of electrons are. So we like to think about things in the position representation. When we have a two-level system, we're not going to pick a representation at all. We're going to stay in Hilbert space the whole time. Okay. What are some things that we know about this wave function or state vector? We know that it has an interpretation, which is that it's to be understood as relating to the probability. All right, so ways of writing that down are to say, for example, if we integrate the square of, let's say, the position representation of the state or the wave function over all the positions, whatever they are, everything. So I'm just going to put R here, everything. That we know that that's equal to 1. It's normalized. Does it have to be normalized? No, but it makes the calculations easier if you do. And in our universe, as far as we know, we call absolute certainty 1. There's an absolute certainty that the particle is somewhere. So if you add up the probability of finding it over everything, you better get 1. Maybe there's a planet out there with people who think that absolute certainty is 2. They probably have integers. So maybe it's 2. Maybe it's 2.6. Whatever it is, they would have a different number here. All of the physics would be the same. Just they would have different numbers. Okay, what else do we know? So I write it in terms of a position. Well, it doesn't have to be written in terms of position representation. How do I represent this in Hilbert space? Okay, so now we have to appeal either to your previous knowledge of this, which would be fine, or to not. All right, so the idea here is very simple. We have a vector space. You can always appeal to conventional Cartesian vector spaces. There's no reason you can't. Hilbert space is related to this. The main difference is it could be infinite dimensional, and the vectors can have complex amplitudes, which they can't do, at least not obviously in this way. Right? But they have components, the Vx component, the Vy component. You learned about things like scalar products, dot product, same thing. We're going to use all that. Okay, so the way we draw, this is simply an artistic thing, but it turns out to be very practical. The way we draw a vector in Hilbert space is to use Dirac notation. I like to think of this as kind of a disembodied arrow sign. So if I have an arrow for my normal vector, the point goes over here, and the shaft goes over there, and I end up with this thing here. Right. This is called a ket. And the dual version of this, which is like the complex conjugate or the Hermitian conjugate, since we have complex things, we have to be able to understand about the complex conjugates. This is called the bra. And that's why this is called the Dirac bracket notation, or bra-ket notation. I guess there's a C in here. Okay, so we represent the vector like this. And the way we can write down that it's normalized is we take the scalar product of the vector with itself, which is what you would do in Cartesian coordinate anyway. And so then to get this condition here, we would say that psi, we can put in, the time dependence if we want. Right, it tells us that the scalar product of the state vector with itself is 1. It's normalized. That's good. And we expect this to happen at all times. We don't want a system to lose probability. That would be terrible. And that's going to give us a constraint on the type of operator that transforms a state from one time to another time. Okay. I keep looking over here, by the way, because my computer with my notes is down here. I could have printed them out, but whatever. Okay, so we have the state vector tells us everything. We have the scalar product, this They understand it to be normalized because it's like it's related to the probability. Here it literally is the probability. This is called the Born interpretation, by the way. Not approximation, that's something else. Born interpretation. And that was what gave us a kind of physical intuition about what the wave function is useful for. Okay, what else do we have? We have to every single observable there is an operator. I'll call it A. A is always going to be the operator, the generic operator for us. And the operator A is a Hermitian operator if it corresponds to an observable. Why would they have chosen that? Well, the reason they choose this is because Hermitian operators are interesting. They have eigenvalue problems, so that if you solve A operating on a function that gives you back that same function times a number, if the A is Hermitian, then that number you get, the eigenvalue, is real. So for example, if A is operating on one of its eigenvectors, phi, I'll call it, I have my own internal logic here is psi is always the state of the system that there actually is. And the other Greek letters refer to bases, right? You probably learned a lot of quantum mechanics where you solved the Schrodinger equation for something, and then somebody said, okay, say that the system is in the n equals 1 state of that thing. All right, so that's fine. But you might have also realized that the solution to the Schrodinger equation to a problem is basically equivalent to finding the coordinate system, right? Just like finding x and y as a coordinate system. And to then say you can only ever be in one of the other of these states is like saying you can only ever walk along the x direction or you can only ever walk along the y direction. Now, why do people say that? It's not true. It's not saying you can't, hopefully no one believes that the only permissible state the system can be in is one of the eigenstates of the Hamiltonian. What can be true is that when you measure the energy, you will find one of the values of the eigenvalues of the Hamiltonian's eigenvalue. But you won't be in, you can be in any superposition of any of these things. They won't be a solution to the time-independent Schrodinger equation, but they're perfectly permissible states. They will be a solution to the time-dependent Schrodinger equation. All right, so just like that, I don't want to make bases any more important than they should be. They are a coordinate system just like this is. To make the point as clear as possible, this is not the only coordinate system I could have chosen for writing this vector in 2 dimensions. Any 2 vectors that aren't parallel to each other could be used to decompose V, right? As long as they're not parallel. That means that they're linearly independent. So there's an infinite number of bases to describe something in 2D. Well, there's also an infinite number of bases to describe any of these quantum mechanics problems. It just so happens, and this is another point about why spectroscopy is so important, the energy eigenvalues are so important that we treat them somehow differently from any other eigenvalues or eigenvectors. All right, well, here's some other operator phi, and it has some eigenvector, eigenfunction, however you want to think about it, and it has an eigenvalue A. Later on, when we do tons of calculations, we'll probably get rid of the phi's and just put the a's inside here. At the beginning, it can look a little messy or a little bit too compact if I just wrote A. That's where we're going, because I'm not going to write phi's all the time. All right, so this is an operator. We don't put hats. You'll know what it is. Of course, a constant's also an operator. But this is the operator. This is the eigenvalue. So this is what we call an eigenvalue problem. Of course, that sounds bad. We don't usually think of problems as bad. But what we really mean is the problem that you solved by figuring out what the a's are and the phi a's. All right, so what we know is if A is Hermitian, and what that means is that A is equal to the so-called Hermitian conjugate, or the adjoint, which is the complex conjugate, but for an operator, then we know that A is real. You can prove this stuff. I can't remember if we do or not. So the eigenvalues of a Hermitian operator are real. And so one of the postulates of quantum mechanics is that when you measure a property of a system corresponding to operator A, the act of measurement, which actually, to be perfectly honest with you, is not very well explained in the formal theory of quantum mechanics. When you do the measurement, you will get one of the values of A, one of the eigenvalues of A. Right? So the way of thinking about that, you have a quantum system, then it goes into an aometer. Here's my little aometer, right? You bought it from Fisher, something like that. Spectrophysics, who knows? You send it into the aometer, and what you're going to get out is you're going to convert that system into one of the eigenvectors of the A operator. We don't know which one. One of them. And the value that you'll have is you'll have an A. So what I'm going to do is try to make a little dial for my aometer over here. I like needles. So these are all the values that it can take, and what you'll do is you'll measure, it'll be one of those values. You measure, you shoot the wave function through again, and the next time you get it, you're going to get a different value. Okay? You don't know which one it's going to be. That's called quantum indeterminacy. You don't know which of the outcomes you'll get, but you know that one of the every outcome you get will be one of the eigenvalues of the A operator. Now, the system may start evolving immediately afterwards, such that when you actually look at it, it won't still be in one of those. Right? That's going to depend on whether it commutes with the Hamiltonian or not. Okay, so that's the basic idea. Operators that are Hermitian can correspond to observables. In practice, a lot of these operators are going to have names that are similar to what they are in classical mechanics. But their form might be very different. For example, although the position, when you work in the position representation, will just be the coordinate, r, or whatever it is, the momentum will not, right? Momentum will be this peculiar derivative of position. If you were in the momentum representation, it turns out momentum is the operator, and position becomes a peculiar derivative, right? And that's related to the commutation relations between position and momentum. Okay. So, I let it. Okay, so we want to know what value you'll get out. And the way you figure that out is you calculate the expectation value. Now, what does that mean? The expectation value is not the individual value that you get. The expectation value is, in some sense, thought of as the average of all the values you would get if you kept doing this over and over again, right? It's analogous to, for example, saying, if I have a coin and I flip it, and it's a fair coin, and I have equal probability of getting heads and tails, and I ascribe some numerical value to heads and tails, like say 0 or 1. So let's say heads is 0, tails is 1. Then we know that if we measure over and over and over again, flipping the coin, we should get equal amounts of heads and tails. Now, something that I always learn something from my kids. And my kids have been learning all kinds of funny facts because their school is crazy and they're doing everything online and they watch interesting TikTok and YouTube videos. And my daughter said, no, the coins are not 50-50. And I was like, what are you talking about? She's like, no, penny. It's like way more heads than tails. And I said, you gotta be kidding me. So I looked it up. Sure enough, it's true. You can look it up for yourself. Abraham Lincoln's head is really round and protrudes quite a bit from the penny. So if you do flip a penny many, many times, I think it's something like 80% heads, 20% tails. I'll double check, and if I'm wrong, I'll fix it in the editing. All right, well, let's pretend we have one of these fake coins that's actually 50-50. Then if you do the measurement, of course, every time you do the measurement, you're going to get either heads or tails. You're not going to get something in between. We're not talking about where it could land on its side. That's something my son would try to do. He's obsessed with trying to get things to land in peculiar orientations. Okay, so you flip it every time you get heads or tails, but since you get an equal number of heads or tails if you do it enough times, the expected value, which will say, let's say, some parameter epsilon will be 1/2. That's very clear. But you're never going to measure 1/2, right? It just means it's the average of doing that many times. So we use that expectation value, And the quantum mechanical recipe for doing this is the following. All right. And that's how we can figure this out. All right, so we're going to get many, many different values every single time we do it. We don't know what we get. We take the average of those, and we're going to have the expectation value.